Hello and welcome everyone to our third of 4 sessions where we will learn from experts on applying complexity methodologies in research. And you can learn about all the sessions by clicking on the link I'm sharing now. My name is Joey Eisman, and I am a doctoral student studying at Temple University and the graduate student representative of the Complexity Theories in Education, SIG. The purpose of the SIG is to apply, advance, and extend complexity theories to inquiry, research theory, and practice in a variety of educational contexts. I am pleased to be joined by Dr. Jonathan C. Hilpert. Dr. Hilpert is an associate professor of educational psychology and learning analytics in the Department of Educational Psychology and Higher Education at the University of Nevada, Las Vegas. He is the current director of the Office of Learning Analytics, housed in the College of Education. His research interests include student motivation, engagement, interactive learning, and other complex, dynamic, and emergent aspects of educational systems. Dr. Hilpert has experience and expertise in a range of research methods, with a particular focus on the collection of and analysis of time-intensive and relational-intensive data for enhancing learning and instruction through the use of analytics. A majority of our session will include Dr. Hilpert's presentation, but if you have questions, please post them in the Jamboard, which I've just shared, or which I already shared. And please join me in welcoming Dr. Hilpert.
Hi, everybody. Thanks for such a nice introduction, Joey. Joey, just before we get started, I know we're working on a kind of a backup plan for audio. So if my audio starts to cut out, would you please let me know, and then we can switch over to the alternative, method that we've developed.
I will definitely do that.
Then you'll see that you'll see I'm logged in with my phone right now. So if we need to switch over to that, just let me know, okay? Let me make sure I've got that muted. Okay, we should be okay. Everybody can hear me all right, Joey? Okay, great. So let me share my screen and we'll get started with this. All right, lovely. So what I'm going to present today is a little bit about methods on social network analysis. And my focus is going to be on how social network analysis methods can be used to make inferences about complex social processes. And the purpose and kind of structure of what I've done here is pretty applied. So I'm going to walk you through some basic principles, and then I'm also going to show you like a running example as I go through. So I'm going to start by covering kind of the process of creating, organizing, and structuring files, and talk a little bit about analyzing the data. And then I'm also going to show you some basic ways to visualize data. I'm going to do that using RStudio, which is a pretty common free piece of software. And I'm going to use 2 libraries, StatNet and SNA. And so for my running example, I'm going to use the movie Star Wars: The Empire Strikes Back. What I'm going to do is I'm going to use these 11 characters for my example, and I'm going to answer this research question. So what I'm wondering is, does the network of characters in Empire demonstrate evidence of self-organization? And self-organization is a fundamental process in sort of complexity approaches, right? So we're going to kind of wonder aloud and then answer the question empirically. Are we seeing evidence of help-seeking behavior amongst the characters in Empire Strikes Back? And my 2 sub-questions are, which characters are most central to providing help to others? Which characters are most central to these self-organizing processes? And then also, could the network have been observed by a random chance? Is this a network that we could have observed in other movies with similar numbers of characters, right, at random? And by answering these questions, we're hoping to be able to produce some inference about whether or not this collection of characters was exhibiting self-organizing behavior, which would be like a hallmark of a complex system. So I'll start just with some basic ideas about social network analysis. And if these are things that you already know or understand, just, I kind of have to kind of roll along with it. But typically when we think about social networks, we represent them in terms of a graph. So here would be an example graph. And this is a network of 6 nodes, right? So the nodes of the circles. And then a series of edges that show connections between those nodes, or in this case, actors. Right? And then these graphs, they can be directed or undirected. In this case, this one's directed because the arrow is showing a directional relationship between the 2 actors. And then they can be binary or valued or weighted. In this case, this one's valued or weighted because some of the arrows are wider than others, so you can have weighted relationships between actors. So for example, in our Empire Strikes Back running example, I'm gonna show you how to create a network of the characters, and we're gonna look at which characters are providing help to other characters in the movie. So if character number 1 is providing help to character number 5, but that help is actually pretty weak, or it actually didn't lead to any kind of success, then the weight of the relationship between the 2 characters would be fairly low. Whereas in this case, if character 5 is providing help to character 2, but the quality of that help leads to a successful outcome, then the weight between the 2 actors or the 2 nodes would be relatively high. So here's an example of a sociogram or a graph, a network chart with 6 nodes and 5 edges. And you can see that this one is binary and directed, right? Because the edges aren't weighted, but it's directed. And we form 2 communities within this particular graph. So we can think about these 2 characters as potentially being one community, and they are unconnected from a second community of characters. So another thing that we can do when we do social network analysis is look at how communities emerge. Right? So when we conduct social network analysis, the basic structure of the data takes 2 forms. The first is an adjacency matrix. And this is a square matrix of relational data where, and you can read through all of this, rows are cases and the columns are the same cases, right? So it's a square matrix. And then the cells represent the relationships between the actors or the nodes. And then these cells can be binary, right? 1 or 0 in the case of an unweighted graph, or they can be continuous. And a lot of times we might be able to measure that continuous data with Likert scale indicators. So in this case,
Dr. Hilpert, your audio dropped again. Actually, now it's muted. Not sure how that happened.
Joe, I'm not either. Do you think has it been going well so far?
To me, it has. It looks like everyone else is giving a good head nod. Yes, so you're doing great. The audio is keeping up.
You just let me know. Okay.
Thank you.
So this adjacency matrix is the underlying structure of the network. Right? And so, for example, in this case, either we have observed using some kind of field experiment or self-report survey that Shannon has not worked with Travis and has not worked with Chris, but has worked with Glenn, right? Has formed some relationship with Glenn, right? And then, and that's what Shannon has self-reported. Let me work right to left, excuse me. Shannon has self-reported that he works with Travis, but not with Chris, but with Glenn, right? And then we can look over here and we can see that Chris has reported that he also doesn't work with Shannon, but does work with Travis and does work with Glenn. So in this way, we can represent social networks using adjacency matrices. The other way that you can, represent social networks using kind of an underlying data structure is through the use of an edge list. And that's a simple data structure where you just have lists of pairs. So instead of having them in matrix form, you would have a list of pairs, Shannon to Travis, Shannon to Chris, Shannon to Glenn, in a kind of edge list format. The social network packages that I'm going to show you today will deal with both formats. But for a lot of reasons, when it comes to gathering survey data, I prefer an adjacency matrix format. So for the data science, underneath structuring and cleaning the data, a lot of the processes that I've set up have been with the assumption that the data are going to be ultimately put together in an adjacency matrix type format. So I prefer that, but the packages will utilize both types. So here's an example of what the two look like together. So we have ID 0, ID 1, 2, 3, 4, 5, and 6 here, and we have them, it's square across the top. And then we have weighted values within the cells to show the relationships between variables. And then when 5 has reported to 6, or 5 has reported to 2, for example, you can see that's weighted at 2, right? And that's here. The other data file that we need is an attribute file, and that describes the qualities of the nodes. So this would be in a standard multivariate type data structure with columns of actors and then rows of actors, and then columns as being the characteristics of the actors. So in this case, we've got Shannon, Travis, Chris, and Glenn, and we have their age and their gender, for example. And of course, I'm sorry, this is a binary conception of gender, so it's probably a bad illustration. My apologies. Regardless, we need to work with both file types, both the adjacency matrix that gives us what the relationships between the characters look like, and the attribute file, which gives us the characteristics of all of the nodes within the graph in order to have a complete analysis. So in this case, our data for our running example for Empire Strikes Back looks like this. So we have an ID associated with each one of those characters, and we give them like a unique ID. And then we have them named a priori. These are the characters that we're interested in looking at. And then we have a quality of those characters. For example,
I'm not sure if you switch screens. We're still looking at the PowerPoint.
It's the kind of feedback I need.
I gotcha. Unfortunately, I think your audio dropped. Really sorry.
No, it's okay. Maybe we'll switch over to the phone and we'll see.
Okay. Fingers crossed.
Okay, can you? Joey, can you give me a thumbs up if you can hear me now? Yeah, so that's working, yeah. Okay, so we're avoiding the feedback loop, but I might need some visual cues if I mess something up because I've got you on mute. Okay, so. Are we still good? Excellent. Okay, So we're adapting on the fly. It seems like it's working. All right, so we got the IDs, we got the names of the characters, and then we have some attributional quality. That's what we call it, the attribute file. In this case, can they use the force or not, right? So C3PO, he can't use the force, he's a 0. Darth Sidious, Darth Vader, they both can use the force, so they're 1s. So we can keep track of the qualities of the nodes through these attribute files that we create. And then we can keep track of the quality of the relationships through an adjacency matrix. So here is an adjacency matrix that I've put together based on my perception of, how the characters in the movie help each other, where you can see that I've operationalized who's helping who and whether or not that help is leading to some success. And so now at this point, you sort of might be wondering to yourself, all right, I get, how Dr. Hilpert could put all of that data together, but what if I wanted to collect it on my own? Like, what if I actually wanted to go out and do a social network analysis on my own and gather this type of data? Yeah.
I'm not sure if you're changed screens again and we don't see the matrix. Is it still just the Excel file?
Nope. So here's the adjacency matrix that you may not have been able to see. And so you can see I have the IDs that align up with the attribute file that I put together 1 through 11 across the side and across the top. And then what I've done is I've created an adjacency matrix that is my perception of how the characters have helped each other in the movie, right? And I've gone through and I've weighted these. But like I said, at this point, you might be wondering to yourself, how would I actually gather this data if I wanted to gather this data in real life, right? So let me give you an example, and this time I'll try not to mess up the share. So here I have an example of a Qualtrics survey that I built. And I've done this with a class before, and so what I do is I just teach this concept. I'll have the students play a character, right? But you can do this for any type of, sort of research project that you might be interested in. I can give you some examples. So I looked at the underlying collaborative structure of my department when I was working in Georgia. I also do a lot of evaluations for NIH centers. And so what we do is we pull together lists of all the people who collaborate in an NIH center to conduct Alzheimer's research or childhood obesity. We also work with a center that works with people who do research on childhood adverse experiences. And they may do research that spans lots of different areas. So they'll do animal research where they'll do studies on how rats gain weight, or they'll collect blood samples from people who come through clinical trials. And so you might have 80 people working together on 3 different, research projects that are focused on all different aspects of, say, how to combat obesity or how to develop a deeper understanding of childhood diversity. And so what we do is we develop surveys very much like this. This is a super simplified version for instructional purposes. But what we're able to do is develop a complete list of all of the people who are in our system, right? So we call that bounding the system. This is often a qualitative step where we'll do some type of artifact analysis, where we figure out all of the people who are working in the center, and then we develop a list like this. And then what we do is we ask them to go through and to check off the people who they work with. And we work very hard to operationalize the quality of these relationships, right? That's critical. So you have to think very deeply about how you define the quality of the edge. So in this case, I would say assign a student a Star Wars name, and then they would enter, I'm C3PO, right? And then they would go through and they would answer this question. Please indicate which characters you helped during the movie. Helped is defined as providing advice or assistance, either verbally, physically, or intrapsychically. And they go through and they choose all the people who they help, right? So you can see what I'm producing here, which is the beginnings of a directed network, right? they're documenting the edges that they perceive to be important to them or that meet the definition of helped. Then what I do is I carry these names forward into a slider question, right? So for example, please rate the degree of help you provided to the characters. Degree is defined as the extent to which the help led to a successful outcome, right? And then you can use the slider to weight the cells in the adjacency matrix. So let me see if I can preview this for you so you can see what it looks like. Joey, can you give me a thumbs up if you can see this? Great. So, like, whoops. Let me go back. Just 1 second. How do I do this? Okay. So I might go in and I might write in, C3PO, something like that, right? And then I would say, okay, I helped Chewbacca and Han Solo and Luke Skywalker. I'm just making that up. And then it carries forward where, okay, I provided help to Chewbacca, but it definitely didn't help him very much. I provided, some help to Han and, that got his ship off the ground. So that was likely to lead to success. And I provided some help to Luke when it came to like translation or something like that, Okay. Now I've entered my data. If everyone who is involved in the system enters data like that, what I'm able to complete out of the back end of Qualtrics is an adjacency matrix that has all of the weighted relationships for all of the ways that I've defined those relationships in the system that I've bound, right? So qualitatively, I bind my system, then I can use a survey type technique like this to indicate what relationships are happening within the system and what the quality of those relationships are. And so we'll define lots of different types of relationships within a particular system. So we'll ask folks, say, how much they rely upon other people to be productive. We'll ask them, who they go to for help when they're having trouble. And we'll be able to spin up these networks that describe what the qualities of those interactions look like. And then we can share them with leaders to show where their communication breakdowns are or who's most central to communication. We also can compare them to, we would consider those to be like, like a posteriori versus a priori type network. So we can look at an org chart and we can say, here's how, from the top down, this laboratory is supposed to be organized. But then here from the bottom up, here's how the laboratory is organizing itself, right? And then do we show good evidence of self-organization? Do we show good evidence of communication flow? And I'll show you what that looks like in a second. Any questions so far?
There are some in the Jamboard, but none have come across in the chat.
Okay, I'll keep rolling along, and we should have some time at the end. So what types of questions can we ask? And we usually, and this is from Crackhard, so usually we would ask research questions at certain levels of analysis. So we can ask research questions at the network level. So what's the size of the network? How dense is the network? How transitive is the network? We can ask research questions at the dyad level. So what evidence do we have of homophily or differential homophily? For example, do we see people who can use the force are more likely to help other people who could use the force versus people who have poor differential homophily? Are people who have the force more likely to help people who don't have the force? And then we can ask questions at the node level. So what is the position of the actor in the network? And for that, we use different measures of centrality. So, but we don't mean that in terms of like a normal distribution. We mean that in terms of like a degree distribution. I'll show that to you in a second. So we can figure out who's brokering what types of relationships, or who's the highest, who has the highest betweenness factor, or who's most central to the network, or different types of sender or receiver effects at the node level. So we would typically organize our research questions at one of these levels. And so you'll see here, I've got this kind of overall question about self-organization. My first question is at the node level, and my second question is at the network level. You know. So the types of questions, you know, they might be, what descriptive statistics describe the network, measures and centrality between this closely, or graph level summaries. Or this question, did the network form by random chance? That's one of the questions that I got most interested in when I first started using network analysis techniques, because you know, I was looking for interesting ways to find evidence for self-organization, and using what's called a quadratic assignment procedure is one of the ways that I kind of like landed on answering that question. And then, is there a relationship between attributes and tie formation, sender receiver effects, differential homophily? Or like we saw in one of these examples earlier here, you know, how many communities form within, you know, in a kind of bottom up way within a particular system. So let me just run through a couple of metrics, and then I'll walk you through some code that will show you how to analyze the data and answer the research questions when it comes to the Empire Strikes Back. So the first is just the density of a network. So how dense is a network? And that's just the proportion of observed ties versus all possible ties. So we could calculate what are all the possible ties that can form in the network, and then see how many we observed, and then divide, and that gives us density. Or we can look at transitivity, and this is the most important sort of piece of evidence for self-organizing processes. You know, I really like work in exponential random graph modeling here by Lusher, because he makes explicit inferences or explicit connections between transitive ties or transitivity formation and complex systems principles. So his book on exponential random graph modeling is amazing. But to calculate transitivity, you would look at the number of closed triangles, the number of triangles that were observed within a particular network, and then you would divide it by the total number of triangles that could be observed. And you can imagine that those numbers get really large. And that gives you a sort of general indication of like degree or clustering cohesion within a network. And it's also at the heart of analyzing community detection or community formation. And then network analysis methodologists have gone through and they've documented what they call a triad census. So these are all the types of triangles that could be observed within a particular network. And then we could look at how often we're observing them and think about what implications they may have on the types of research questions that we might have, or the types of observations that we're trying to make. So you can see all the way down from, you know, no tie formation at all between 3 to just having a director relationship here, to having like an information sink, right? Or someone who's just providing information to other people. There's lots of different ways that you can operationalize these triangles and make inferences about how communication is flowing, or how help is you know, being provided. And then you can also look at dyads, and these are pretty typical. So this would be what we would consider like an out degree, where A is helping B in our case, and in degree where now A is receiving help from B, or a mutual tie where they're helping each other. And we'll see examples of all of those here. And then you can run different types of analyses, again, within the ergom framework, to see if there are certain types of attributes that might be related to the observance statistically of these kinds of in degree or out degree. So like, again, are people who have the force more likely to send a tie when it comes to help seeking as opposed to receive a tie, that type of thing. And these give you an idea, just to keep trying to bring it back to complexity principles, but what are the kinds of micro level processes that are underlying the emergence of macro level indicators of the system, right? So we think about complex systems as being sort of like micro level interactions amongst different agents that, you know, produce emergent macro level outcomes. And so when we're looking at these little individual indicators of relationships between people, and then we see how they emerge into some, you know, systems level or some network level sort of phenomena or organizing structure, we're making inferences about how the complex system is functioning across multiple levels of analysis. And we're making those inferences about not causal mechanisms, but emergent mechanisms, right? Self-organizing processes. So again, just quick some definitions: homophily, a shared characteristic; betweenness, so you can see Shannon here as the highest level of betweenness because the degree distribution for this node is 3, and that's the highest degree distribution in the network, right? And then I'm going to make some points later about this, but let's go ahead and get to some analysis. Let me stop my share and then restart it. Okay, so here's some basic R code that I put together for this presentation. Let me move this toolbar. And I'll just walk you through it really quickly. I don't know, sometimes people get bored by code, but I don't mind taking a look at code. So I hope you don't mind just kind of like walking through it. I'll go fast. You know, I know it's not the most exciting part, but it's useful and I'm happy to share it. So I'm in R, this is our studio right now. And then, you know, I'm calling this Star Wars analysis. I'm using 2 different libraries to analyze this data, StatNet and SNA. You can look those up and look at the, you know, look at the packages and the functions and stuff that I'm using in their documentation. They're super common for social network analysis. Other people like to use like iGraph. iGraph's nice, but I only teach iGraph when I'm teaching like advanced visualization. So, and I'm not going to do that now. So. And here I'm just setting the working directory. So I'm setting that to my desktop. So I'm basically just telling R, you know, take a look at the folder on my desktop named SNA complexity SIG for the data files that I want to analyze. And then what I'm doing here is I'm reading the network in and I'm converting it to a data frame. So that's this CSV that I showed you earlier. Stop share, reshare. Right, this is the data file that I'm actually reading into R, and it's just the underlying adjacency matrix. And this is the data that I had you imagine that I collected using that survey, right? Where I have the relationships, who helped whom in the cells, and then I have them weighted with the degree to which they led to some success. And stop share. So this little tool, so you can see I'm just reading this in. It's got 11 observations. If I look at it, it looks exactly like the data that I just read in from the CSV file. Just close that. And then now I just have to do a couple things. You can read about this in the StatNet package, but I have to convert it to a data frame that is a matrix. So all this does, and I'm just naming it .m, because I need to tell R that this is a matrix and that it's square. And then I have to transform that into a network object, which is a class of object that StatNet uses. I can tell you that when I first learned to use this package, like, I don't know, 8 years ago, 9 years ago now, these 3 lines of code took me longer than anything else. I could figure out how to get the thing ready, you know. And then what I always do is just make a plot. So I just plot it right away, no labels, no anything, just to make sure that it meets like the sort of like visual inspection test. So here's a quick little plot down here. And then I just want to know, is it valued? And the answer is true. And then this just gives me an idea about whether or not what I've read in is actually matching what I think I've read in. It just gives me a little bit of a test to make sure, plotting it and then checking to make sure that it's valued. And then now what I have to do is I have to read in my attribute file. So this is the attribute file that I just showed you earlier. Stop share. Reshare. So this has my IDs and my names, and then, do they have the force or not? So I'll go ahead and read that in, and then you can see that my attribute file has 11 observations of 3 variables, and it looks exactly like what the CSV file I showed you. And then what I'm just going to do is check the variable head to make sure that I've got an ID, a name, and then a force category in there. And then I won't look at the whole attribute file. Usually I check the head because a lot of times these lists are long, so I just want to look at the first 5, right? If I see the whole attribute file, my output gets full of data that I don't necessarily care about. And then now what I'm doing is I just wrote a little line of code that checks to make sure that my IDs are in the same order as the adjacency matrix. So what it does is it goes through and it just marks true if the ID in the first row is in the attribute file is the same as the first row in the adjacency matrix, and it looks like I'm good there. And then what I'm doing is I'm linking the attribute file to the network object. So now it knows that within this particular network, node ID1 is C3PO and he can't use the force, right? So it gives me the attributes connected to the edges. And then now I can plot and I can put the names in. So, and these you can go like on and on with this code if you want, but you can see I robbed this from another line and it's named family and friends, and I'll call it Empire Help. And then you can adjust the size of the nodes and the edges, and, change the column names to call different things. And this plot function is using a layout algorithm by default, and you can go in and change the layout algorithm. I think this one's called like the Fuchterman Gold layout algorithm, which is one that I actually like quite a bit by default, but there's plenty of different layout algorithms for figuring out how, you can make them circles or you can make them however you want. And there's a whole, sort of like, area of study on layout algorithms. That's pretty fun. So now I'm just calculating the measures of centrality for all the characters in my movie. So, I'm first going to run this, just, the degree. So this is going to give me degree for ID1. So C3PO's degree is a 3. The degree for ID2, Chewbacca, his degree is a 4. Okay. And then now I'm going to do those by in and out degrees. So now instead of just whether or not there's an edge, it's going to be how many are coming in versus how many are coming out. And we get some different output there depending upon, because we have a directed weighted network. So depending upon whether or not they're going in or out, we get the raw variables there. Now we're going to measure this notion of betweenness. And so this is which character is most between to the help seeking network, right? Which character is most between, and it produces a calculation. And you can see that this person, it looks like 1, 2, 3, 4, 5, person 6 is the most between in the network, right? So I can go and I can see that the person most between was Lando Calrissian. Well, that makes a ton of sense because Lando was double crossing everybody in this movie. He was working with the Empire, he was working with the Rebels, he was working with Han, he was working with Darth, and he was helping them both, right? So I can find out that, that Lando was the most between in my, self-organizing processes. The movie was essentially reliant upon his double crossing, And then I can also measure closeness. So this is a measure of who was not the most between, but who is the closest to the most between character, right? So this is like, who's the VP of, the king of betweenness or something like that. You can see, I can go through these statistics. So I can see that this person and this person are tied. So that's ID 1, 2, 3, 4. So Darth Vader, right, is the most close to Lando, and he's double crossing. And then 4, 5, 6. Yeah, so Lando. So you can see that the closest person to the most between character was, the main bad guy in the movie, right? Okay. Good illustration for teaching purposes, I think. If you haven't seen the movie, you might be lost, but you should go watch it. So now I'm moving on to my network summary characteristics. So now instead of looking at the qualities of the individual nodes in the network, I'm looking at the qualities of the network itself. So you can see the size of the network is 11. That means I have 11 total nodes. You can see that the network edge count, how many edges did I observe in the network? 27. So I observed 27 help seeking or help providing relationships in the network. Here's the number of dyads. The number of pairs that I observed was 110. So that's a lot of dyads. That's, these, like I said, these numbers get big. And then here I'm calculating density. Oh, I'll slow down. So you can see that these are all functions, right? I forgot I'm teaching some code here. So all of these are functions in the package, SNA and StatNet, right? And so I write the function and then say betweenness, for example. And then I've also created my object, my network object, which is net C1, right? And then I'm giving you the node here, the mode of the network, In this case, I'm seeing that they're undirected and they should be directed. So I'm going to make that change real quick. Let's see if it changes it. So in my network size, network edge count, these are all functions that come in the package. And then there's documentation on how all of these calculations are created in the package. And you can go look for yourself if you're curious. But now I'm interested in the density of the network. So you can see the density of the network is 0.245. So that means because I'm dividing the number of edges that I observed versus the number of possible edges, 25% of the edges have formed, And these density statistics are super interesting for making comparisons over time. So we can track network density over time. Let's say we decided we were going to window the movie, and every 15 minutes we were going to go through and make an observation about, who was collaborating with whom. Then we could see an evolving sort of system of helping, and we do a lot of that with network analysis where we'll window our observations over time. And then we'll look at changes in these statistics at the individual level or at the network level to make inferences about how the system is changing. And then here's our transitivity calculation. And you can see that's 45. So we have a relatively transitive network. We've observed 45% of the possible triangles that we could have observed. And then if you remember on that slide, I don't want to go through the process of sharing and resharing again because I'm running out of time, but the triad census. So I showed you all of those possible triads, right? All the possible triangles with their different shapes, and they were labeled, 003, 021, 102. So 003, if you remember, was no relationships, right? So we observed 32 of those, right? 32 triangles that we could have had that we didn't, right? And we got 63 of this type and 18 of this type and 9 of this type. So you can take a look and see how many different types of relationships or the types of triangles that you've observed and, make inferences about the frequency or the quantity in which you're observing those. Okay, and then so finally, so we answer our first research question, like, which character was most central to the help seeking? And our answer to that question was Lando Calrissian. And we were also able to, because of our knowledge of the system, know that that's because he double-crossed everybody, right? He was working with both sides. And then now we're wondering, could we have observed this system by random chance, right? Is this a self-organizing system that is emergent, or is this a system that we could observe anywhere just by random chance? So in order to do that, we're going to create a random network. And the way that we're going to create that random network is we're going to use this rgraph function, right? And we're going to create a random network that has the same number of nodes, 11, and then the same probability or density of tie formation, right? So our net1 is the object that I'm going to create over here in my global environment. And then, so now you can see that this is, well, it's a vector now, but now it's a network, and that network has the same number of nodes and roughly the same number of edges because it has the exact same density as the network that we observed in the movie, right? So I just simulated a network. So you can see I'm going to plot my network versus my random network. And we can make some visual comparisons between what the random one looks like versus what the one I observed looks like. And you can see that I have some tighter clustering, right, in the one that I observed. Like I immediately see that. And then I can do dyad and edge counts on both the random and the network, the random and the observed. So I gotta move this little tool. And you can see that I have, which one did I run here? So this one you can see for the for my first set, I observed 110 dyads with 27 edges, and then for this one it was 110 dyads with 25 edges. So I have two very equivalent networks on my hands, right? Okay, great. Now I'm going to run edges. I'm going to run just some summary statistics on both of these networks using the summary function. And what you're going to see is in the network that I observed in the movie, I saw 31 triangles. But in the network that I created randomly, I only got 11 triangles. And because what we know about the self-organizing behavior of systems, the formation of transitive relationships within the networks is prima facie evidence of self-organizing behavior. I don't observe those by random chance. I only observe those within self-organizing systems. So what I've done is I've created a random network, and I'm seeing like triple the amount of triangles within that network that I observed than I would expect to see by random chance. And then I can run what's called a QUAP test, which is a quadratic assignment procedure. And this is essentially just a statistical test that tests the equivalency between the two networks. And if you want to know the details of that, you can look all that up. That's probably more boring than the code. And what you'll see is that my F statistic comes out less than 0.05. And I ran this like 3 minutes before I got into this meeting. I ran it a few times just to make sure I was producing the significance value that was gonna, but it replicates. So I've produced 6 or 8 of them, and you could loop this code and you could simulate 1,000 of them and run this test 1,000 times. I've got 1,000 reps on this one right now, but it could be 10,000, just depending upon how much. Sorry, my dog just came up. Just depending upon how many you want to simulate, how much comes through. So that's the answer to our second research question, which was, does our network exhibit evidence of self-organizing behavior? And the answer is yes. All right, that's pretty much all I've got. I've got 2 more points to make in conclusion, and then we'll open it up to questions. So then I guess the sort of question is, why is this complexity? And there's 2 points I want to make here. The first one is, like, what's fundamental to me about studying complex systems at the most basic level is that we're observing dependent relationships between people, technologies, constructs, whatever it might be. Like, we've abandoned the independence assumption. We're interested in why things are connected, as opposed to making the assumption that they're not. Right. And then the second is that we can make inferences about macro level self-organizing emergent processes from relationships that we've observed between the micro elements. So we can look at these micro level behaviors amongst actors, and then we can use that to generate evidence for macro level, system level qualities that have implications for whether or not this is a good movie, or what kind of policy we may want to put in place to help a school. There's a million things that you can do with complex systems, but at its heart, these are the 2 points I kind of want to finish with. So with that, I'll kind of open it up for questions for the last 8 minutes or so.
Well, first of all, thank you so much. This was very enlightening and useful and meaningful for me. I also am a big Star Wars fan, so I really appreciate that.
Yeah. Like my 12-year-old son's sitting over here and he's laughing like while I'm talking. He likes Star Wars too.
I'm sure he and I have a lot in common. I'm going to share my screen and show you some of the questions that came up. I don't think we'll be able to get through all of them, but I'll let you decide what is meaningful to you. There's kind of an array of questions. They're all in orange.
Yeah, gosh. Okay, how can we get your code? I'll just share it in a Google Drive. I'll just give it to Joey.
Yeah.
And then
I can send it out. We can send it out after the fact.
I'm happy to give away all of that. Is there a scope to understand SNA on interaction clickstream data? Yeah, the method I've developed is a Markov process. So I develop individual networks for clickstreams. So instead of a lot of people analyze data on discussion boards and stuff like that, and I felt like that's done. So what I've been working on with clickstream data is doing like a Markov modeling on the clickstream itself. So a student may click through a class, like 1,000 times or 100,000 times over the course of the semester. And when they click on different elements within the LMS, so they click on the calendar, then they click on the homepage, then they click on a quiz, what I can do is develop a network of probability transitions amongst those elements. And it turns out that the network qualities of those probability transitions are highly predictive of grade. And we're trying to get something out in BJET right now on that. So I hope you won't scoop me on it, but even if you did, I wouldn't care. And I'm happy to share, whatever. But that's what I'm doing with clickstreams. That's the feedback into complexity theories. Have any theories been empirically confirmed this way? Yeah, so I mentioned Lusher. That's my favorite. His book on exponential random graph modeling just talks really in depth about mostly about different triadic or star-like formations that you can observe within networks and how those are evidence of complex systems. Interactions of identity components. Yes, like I think maybe what you mean by that is by looking at the relationships between like latent constructs. So let's say I measure self-concept and self-efficacy and self-regulation using surveys or something like that. Instead of doing a factor analysis or confirmatory factor analysis, I can use something called mixed graphical modeling, MGM, really amazing alternative where you're looking at the networks amongst latent constructs that you might use to measure identity or motivation or engagement using a kind of like survey type framework. I think that's what that question means. Have I conducted network analysis where nodes are not people? Yes. So clicks or latent constructs, they can be anything. Yes, not just social network analysis, but for an instructional tool, I think people use like people get SNA, like that way. But yeah, and then we also, for the NIH laboratories, we measure interactions between people and then also machines. And so for example, if there's a tool that can conduct assays or that spins blood and produces results that way, whatever the fancy machines are that all these people use that we work with, we get the names of those machines and we ask them how they interact with those. And then I take from Mario Bunge here, who's a philosopher who talks a lot about complexity theory and about how people and technologies and tools all interact to create systems. And so we draw up these network maps of who's working with whom around what products and using what machines. And we show those to lab PIs and they fall all over themselves because they can immediately tell where the problems are with communication and interaction. They're really helpful. Tips on how to build animations. Yeah, okay, so StatNet and SNA, there's both are connected to a package called ergum, which is a technique and a package, and then there's like a t-ergum, and in t-ergum, there's a function that will allow you to do dynamic visualizations of graphs, but it's pretty bad. I mean, it works, but it's not exactly like, 4D. And then there's also like Gephi does an okay job with dynamic visualizations, but it's also free and buggy, so you have to fight with it a lot. Is it only survey count data? No, we use observation data for sure. You can observe playgrounds. I've observed a lot of classrooms and done SNA analysis with classrooms. And then, so that's great. Artifact analysis is really terrific too. You can do a qualitative analysis of artifacts and spin up networks that way and produce really amazing data. I don't know what a Girvan-Newman cluster analysis is, but I do use like a lot of different types of like walk trap algorithms to do community detection, and that's always pretty helpful. You can see clusters within the network that form, in emergent ways. And essentially what that does is it's a random walk through the network, and then the algorithm calculates where the information gets stuck, like where it starts to spin. And then it says, okay, these nodes are a community. And it does that. And then, ultimately it tells you from a kind of bottom up method, what, how many communities it thinks there are where information is getting stuck.
Dr. Hilbert, I think we lost your audio, weirdly enough. Dr. Hilbert, I think we lost your audio. Oh, okay. Dr. Hilbert, we lost you. If you can hear us, we lost
my phone audio feed.
We must have lost your phone somehow, but I actually want to say that we've hit time.
We're right at the end, so hopefully I can respond to that last question. It gets harder for for illustration purposes, to be able to confirm the double crossing that we saw in the movie was a really nice teaching tool. But you could go in and you can use the triadic formulations around Lando, right? So I can go look at Lando, and then I can figure out what type of triadic formations he has around, say, different attributes, good guys, bad guys, right? And then I could say Lando is at the center of this, and he has this many out degrees going to both good people and bad people in the movie, and I would have empirical evidence that he's double crossing. But we're trying to, he's playing both sides, right? And then there's also something called a brokerage analysis, which is I like the Fernandez-Gould method here. Ferdinand Gould, something with an F Gould. And it was produced in 1989, and it does really nice brokerage analysis where it shows you around different people, which types of transitive relationships they're involved in. So you can see who's brokering what types of relationships. And then we could produce evidence without the movie that Lando was double crossing or playing both sides.
Wow. Amazing. Well, first,
so thanks for that question. It's a really good one.
Yeah, thank you. And first, please join me in thanking Dr. Hilpert for this rich and meaningful discussion and conversation today and presentation. Thank you. That was wonderful. Please join us for our next session, Monday, April 3rd at 4 p.m. Eastern Time, where Dr. Bullock will present on complexity-informed mixed methods, data collection procedures, visualizations as a tool for developing instruments and protocols. And you can register for that webinar using the link I just put in the chat. And for everyone who has joined us this evening, thank you so much, Dr. Hilpert, one more time. Thank you so much for presenting to us today, and we hope to see you at the next webinar. Have a good night, everyone.
Thank you, Joey. Like just one thing, I really appreciate you kind of rolling along with some of those problems. Really, really, really awesome. Thanks for the opportunity.
Pleasure. Tech issues always happen.
Email me if you have any questions.